Welcome. Today, we're diving into Boolean algebra and logic gates. This is the foundation of how computers think and make decisions. We'll explore the basic concepts, starting with Unit 1, and see how these ideas power everything from simple circuits to complex systems. Let's get started. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Logic gates are the foundation of all digital circuits and computers. Think of them as tiny electronic switches. They take one or more binary inputs, zeros and ones, and then, following specific logical rules, produce a single binary output. These simple building blocks combine in countless ways to create everything from basic calculators to powerful processors. Understanding logic gates is the first step to grasping how digital technology works at its core. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's break down the three main types of basic logic gates. First, the AND gate. It only outputs a 1 when all its inputs are 1. If even one input is 0, the output flips to 0. Next, the OR gate. This one outputs a 1 if any of its inputs are 1. It only outputs 0 when every input is 0. Finally, the NOT gate, also called an inverter, it takes a single input and flips it. So a 1 becomes 0, and a 0 becomes 1. These are the building blocks of digital logic. Let's talk about universal gates, specifically NAND and NOR. These gates earn their name because you can build any digital circuit using just them. The NAND gate is like an AND gate flipped on its head. It only outputs 0 when every input is 1. On the other hand, the NOR gate is the opposite of an OR gate. It outputs 1 only when all inputs are 0. Together, these gates form the building blocks for any Boolean function we need. Now let's look at special purpose gates. The XOR gate, or exclusive OR, outputs a 1 only when the inputs differ. That means one input is 1 and the other is 0. If both inputs are the same, it outputs 0. The XNOR gate is just the opposite. It gives a 1 when the inputs match, both 1s or both 0s. These gates are key for comparing signals, and they play a crucial role in digital logic. When we implement a Boolean expression with logic gates, we're turning abstract algebraic variables and operations into a real physical circuit. It starts by simplifying the expression, so it's as clear and efficient as possible. Then, we identify each operation and, or not, and map those to the corresponding gates. Finally, we connect everything, from the input variables through the gates, all the way to the output. This step-by-step process lets us build a working logic gate circuit from an equation. Let's break down the process of implementing a Boolean expression step by step. First, always simplify your expression using Boolean algebra. Fewer terms means fewer logic gates. Next, follow the order of operations. Start with NOT gates, then parentheses, followed by and finally OR. Begin your diagram by placing input variables on the left, adding NOT gates where needed. Then, group multiplied terms with AND gates. Lastly, combine all those AND gate outputs with a single OR gate to complete the circuit. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. The NAND gate is special. It's called a universal gate. That means you can build any digital circuit or Boolean expression using just NAND gates. To do this, we start by replacing the basic logic gates with their NAND equivalents. For example, a NOT gate is just a NAND gate with both inputs the same. An AND gate is made by NANDing the inputs, then NANDing that result with itself. And an OR gate, that's two NOT operations followed by a NAND. With this approach, NAND gates become the building blocks for everything. Let's break down how to create a NAND-NAND logic diagram from a Boolean function. First, we simplify the function and write it in sum of products form. That's where the function is expressed as ORs of AND terms. Next, for each product term with 2 or more literals, we draw a NAND gate. These form the first level of gates. If there are any single literals, we also draw NAND gates for them. Finally, all outputs from these first-level gates feed into a single NAND gate at the second level. That's the basic structure. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about how to build an AND function using only NAND gates. NAND gates are universal, which means we can create any logic operation with just them. To get an AND, we first feed the inputs into a NAND gate, then take that output and pass it through another NAND gate configured as an inverter. This double step flips the NAND's output back into the AND result we want. It's a clever trick, using just one type of gate to do so much more. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Now, let's look at NOR gate equivalents. These are alternative ways to build the same logical function using different gate combinations. Understanding these equivalents helps us simplify circuits or adapt designs based on available components. It's a powerful tool, knowing how to swap one gate for another without changing the outcome. This flexibility is key in both theory and practical electronics. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth.
Please do like, share and subscribe my channel. Thank you for watching.